Hello everyone, welcome to one more episode of live discussion. Today I again welcome Mr. Ashwini Kumar Sinha ji and Suresh Dwivedi ji for this discussion. Today our topic of discussion is blockchain technology and low cost processors or single board computers for blockchain. My first question is, what are the minimum hardware requirement to run a lightweight blockchain node, and how would you meet them on low cost processor?
Yeah, so for the low cost requirement, if you want to set up a low cost based blockchain node, there are lots of low cost SBC single board computers or single or processors are available there or there. So the minimum requirement is at least you need for the blockchain node for the Bitcoin or Ethereum or private chain, these kind of things. You minimum requirement is the 1 gigahertz single core processor that is greater ARM Cortex A7 or better one, or you need a from 512 MB to the 2 GB of RAM. Okay. You need a 5 GB to 2 GB of sorry, 512 MB to 2 GB of RAM. Okay. And uh, and for the storage size, you need the 4 to 32 GB of RAM. So this is the minimum requirement that you need. For the network side, you need at least of a stable internet of 9 to 10 Mbps, syncing the data and transmit transactions. So these are the minimum requirement that you need in the processor for the black block for establishing the blockchain node. And there are lots of options are SBC options are available there to establish such as low cost and high decent performing affordable nodes. One is that well known that all of you have known about it, is that is no other than the Raspberry Pi 0W. It cost you around $15, and in Indian rupees it's around 1,500 rupees or something like that. Okay. And it gives you the basic it meets the basic requirement for the blockchain node, that the 512 MB of RAM and the quad core or Cortex A53 ARM Cortex processors. Okay. You can go the better version of Raspberry Pi as well, like 452 as well for the better performance. But this is a basic requirement that SBC that meet the requirement of the blockchain node. Okay. And there are similar few SBCs are also available, like the Orange Pi and similar like that.
Okay. Okay. How does blockchain consciousness impact hardware selection and energy design?
Yeah, actually, blockchain consensus mechanism like proof of work (POW) and the proof of stake (POS) significantly influence hardware selection and the energy consideration. First, talk about the proof of work (POW). Actually, POW requires solving complex mechanical problems to validate to validate the transactions and the create new blocks. This process, called mining, demands high performance hardware, mainly application specific integrated ASICs are graphic processing unit, normally known as GPUs. These components offer the necessary computational power but consume a large amount of the electricity. As a result, POW system lead to a significant energy usage and the heat generation, requiring efficient cooling and the high energy infrastructure. Bitcoin, the most well-known POW blockchain, has faced criticism for its environmental impact due to its massive energy consumptions. So, Now we discuss about the proof of stake. POS normally it contrasts, select, validates based on the number of coins they hold and are willing to stake as a collateral. So POS eliminates the need for the intense computation, thus drastically reducing energy consumption. It requires only the general purpose computers or servers, not high-end hardware. Ethereum shift from POW to POS. Ethereum 2.0 reportedly cut its energy usage by over the 99%. So actually, what is the impact? In POW system, the need for the specialized power-hungry hardware shapes systems design around power efficiency, heat management, and the scalability. In POS, energy design focuses more on the network security, uptime, and the reliable connectivity rather than the raw computing power. So, in summary, POW demands energy-intensive specialization hardware, while POS enable energy-efficient systems with more flexible hardware options. The choice of the consensus mechanism thus drives the fundamental decision in blockchain hardware and the energy design.
Okay, so how would you design a hardware wallet or secure enclave for private key storage on an SBC?
Yeah, so for the SVC like Raspberry Pi and all those things, when you make a blockchain node or the Bitcoin and Ethereum or some similar kind of technology. So yeah, so for that you can use the dedicated secure element like yeah, just a second. My camera is getting a little bit of lagging. Okay, yeah. So it's connected now. Yeah. So you can use the dedicated secure element like ATEC60B that cost you $1, and you can connect with your SBC like Raspberry Pi using the I2C or SPI bus, and you can use the parallel encryptions or secure boot. You can use the security elements like AES 128 or 256 encryption to your system, and you can integrate all those things on the Raspberry Pi. Like we have I've already told you that it is a better and very low cost, affordable, and so that is the lowest affordable cost that you can blockchain node that you can create. That one I have here also created here based on the Raspberry Pi. Here you can check. This is also one of the blockchain node. Okay, so it uses the Raspberry Pi, and as the Suresh sir have earlier told you, it creates a lots of heat when working with those blockchain nodes. Then you need a certain kind of cooling. So I have included the water cooling here with the with here water cooling technology on this, and this whole node is using the Raspberry Pi. You can see here it's the Raspberry Pi, and it is whole thing is water cooled. So it's a simple blockchain node that you can create with the Raspberry Pi with the cooling and all those things. And for the secure element and the hardware wallet or secure enclave and private key storage, you can integrate ATEC60B, and you can also use the AES 128 or 256 encryption. You can also use the secure boot, and you can you can also add many other security layers if you want to add. So that's all.
Okay. Okay, so what are the input, output, and storage design consideration when deploying a full node on a resource-constrained device?
Actually, yeah. When deploying a full blockchain node on the resource constrained device, input and output and the storage design play a critical role in ensuring stable and efficient performance. First, storage is one of the biggest challenge. Full nodes need to store the entire blockchain which can run into the hundreds of the gigabytes depending on the network. On low capacity devices, this is not practical. So enabling pruning is must. It allows the node to discard older blockchain data while retaining the latest state needed for the validation. So using a high endurance SSD or industrial grade SD card is preferable, and frequent read-write operation can quickly degrade low-quality flash storage. And the second, input-output performance must be optimized to handle the continuous database reads and the write block chains. Nodes typically use label IDB or ROXDB to store block and the state data. They need tuning to reduce disk sizing, especially when RAM is limited. Also, minimizing log verbosity reduces unnecessary disk write and improves I/O lifespan. And the third is the live file system and the storage format also matters. Lightweight file systems like ext4 with journalizing disabled can help reduce overhead. So enabling compression can save space but may add CPU load. This needs balancing based on the device spaces. On the network output input side, peer communication and block propagation consumes bandwidth. On the limited system, it's useful to cap bandwidth usage, reduce the number of active peers, and the schedule syncing during off-peak hours to avoid totaling or the power issues. Lastly, catching it constrained due to the limited RAM. So it is important to adjust the node's cache size for the optional use without exhausting memory. Monitoring tools should also be lightweight to avoid the adding overheads. So in short, deploying a full node on the constrained hardware require a careful trade-off between the performance, durability, and the resources usage, mainly through the pursuing tuning and the efficient input-output handling. That's all.
Okay, so how would you handle cryptographic acceleration on a low-cost microcontroller or SPC without dedicated hardware support?
Yeah, like I have told you earlier that we can use the cryptographic accelerator, or we can use the dedicated hardware like uh, uh, ATECE secure boot secure element chip on the SBC, like that. But here, if you want to remove this, you want to remove the dedicated one, you want to use the direct things on the SBC itself, then you can use the cryptographic capability of the SBC, like Raspberry Pi, that CPU supports with the Neon SIMD instructions, which accelerate the cryptographic operations. And there is no need of dedicated hardware here, hardware engines like okay. And on software optimization side, you can do SHA 256 Neon optimization. You can enable these settings in the software side. In the Neon acceleration, by enabling the Neon acceleration in the compilers, it can polarize the SHA 256 and ECDSA operations, and can achieve the speed of 10 to 20 Mbps per second, MB per second, and 5 Mbps without the Neon. Okay, so this is a difference between enabling the Neon acceleration and without. Then you can go for the code stripping as well, and you can also use the even though question is not is about not to using the dedicated, but it's better to use the dedicated secure element, external secure element like microchip ATE CC60B that cost $1. You can attach it via one I2C, and you can also do the multiple multi-threading between the different layers of cores in the SBC available. You can also make a combined node, like one, like what you call super cluster, supercomputer cluster or Raspberry Pi cluster. You can use that thing as well. Like this is the one node that I have created, so I can combine make two different nodes with this and clusterize them. We can parallelly connect them, and they can share the tasks between each other. Okay, half tasks. So you can also do that pipelining, parallel processing, or multi-cluster combination. You can do those cluster pi and all those things as well.
Okay. So, okay, so what interfaces would you use to connect sensors or actuators to a blockchain-enabled SBC in an IoT environment?
Yeah. Yeah, in blockchain-enabled IoT environment, selecting the right interface to connect the sensors and accurate to the single board computer SBC is essential for ensuring reliable data collection and the control. Firstly, GPIO, General Purpose Input Output, is the most straightforward interface, ideal for basic digital sensors, switches, and the simple actuator like LEDs or buzzer. It offers direct control with the minimal configuration, making it great for the low latency task. Secondly, I2C, sometimes known as I2C, is widely used for the connecting multiple low-speed sensors such as temperature, humidity, or the pressure sensors module. It uses only two wires, SDA and the SCL, which simplifies wiring and make it well suited for the compact design. And the third is the SPI, Serial Peripheral Interface, is preferred when the higher data rates are the needed, like within the certain ADAs, displays, or the memory modules. though it uses more pins than the I2C, it delivers faster and the more stable communication. UART is the another key interface, especially for the communication-based modules like GPS, GSM, ZigBee, or the LoRa. It's commonly used when the sensors or the actuators need to communicate over a serial protocol, including connections to other microcontrollers or the external boards. For more advanced are the industrial application, RS485, Modbus, and the CAN bus are the critical. There are robust long-distance protocols used in environments like manufacturing or the smart grids, where the electromagnetic interference is a concern. So, if you are integrating cameras or the high-end peripherals, USB is also an option, though it comes with the higher power consumption and many requires delivery. So, in many cases, analog sensors require an external ADC modules connected to the I2C or SPI, since most SPs do not have the built-in analog inputs. So ultimately, the choice of the interference depends on the sensor's type, communication, speed, distance, and the power constraint. Once connected, blockchain ensures sensor data integrity and the actuator locks are the securely and the recorded and the tamper-proof. That's all.
Okay, so how would you implement secure firmware updates on blockchain-based embedded system?
Yeah, so for the like we are considering with from the starting of the discussion regarding the Raspberry Pi. So let's take the example of the Raspberry Pi. So for getting the secure boot mechanism, you can use the U boot that is common in the Raspberry Pi with the secure boot enabled firmware. And you can also check the and verify the integrity of the firmware that is SHA-256 hash against the blockchain store hash to ensure it has not been tempered before. You can apply the update with the new firmware secondary flash partition, and you can put a dual blank setup to allow the rollback of the update if the update fails. So we have the partitions that once the new firmware come, and then after the establishing of the new firmware, verifying the new firmware, the previous firmware got deleted or the got removed from the memory. Okay. So if suppose that incoming firmware fails, so I am making update on the device, and if I have the partitions of that thing, then I have the old firmware right now. It didn't get deleted because I'm getting the new firmware updated from here. So if by chance the new firmware that I am updating from here got interrupted or somehow get filled, then still I have the chance to roll back to the previous firmware because it's already there because in the partition. So using this kind of partition technology can help you in that. And for the secure boot, like I have already told you, in the Raspberry Pi, you can configure the U boot, and you can configure the secure boot, enable the all those things in the inside. And in the if you can also use the you can verify the firmware signature using the public stored in one time programmable, that is OTP, one time programmable memory, one time programmable OTP memory, or secure element like ATCEG60B. I have already told you earlier. And you can use this kind of secure boot, secure element with that. Okay. So this is how you can also add the error handling and recovering part in that whole system setting. Okay, like and verifications of failures, and all those different layers out there.
Okay, so how would you integrate blockchain with real-time operating system, RTOS, and what are the timing and memory challenges?
Yeah, so in RTOS is generally you can find it in the microcontrollers like ESP and similar microcontroller, ARM Cortex, low-level microcontrollers. In the Raspberry Pi, it's a different thing. Okay, so let's take about the regarding that. So for the IO RTOS, you can use the lightweight RTOS like the pre RTOS or J per RTOS JEPHR, what we however you could pronounce this. So generally one of the most common is the pre-RTOS one that will be used, and both takes you around 10 to 15 KB of footprint for the real-time task and sensor sampling actuator control. You can run the RTOS alongside with a minimum Linux distribution as well, like in the Raspbian Lite or for the blockchain operations. Okay. So on the OS side, you can do the configuration like hybrid approach. Like you can run the RTOS as a dedicated thread of or core, uh, and under the Linux, and use the real time patch or a bare metal application on one other core, or bare metal or RTOS for RPi 0. Like you can run the RTOS directly for the minimum, determinized and blockchain task and priority process. So you can set the priority task high, and in the RTOS, generally how the things is work. It's not like the multiple threading you can call it threading, but it's not the actual threading. Okay, so it's what do RTOS real-time operating systems. It is not actual the threading parallel processing. It's just a switching between the task and very fast switching. So RTOS, how the RTOS works? It gives it's divides the tasks into the high priority tasks and the low priority tasks. So you can in the software structure of the RTOS task, it's first execute the high priority task, that a real-time task like sensor pulling with the 1 milliseconds intervals, or actuator controls with a strict deadline that it have to complete that particular task in this deadline, and that task is high priority. It has to be executed first, and then it comes the low priority task, that like the blockchain operations, transaction validation, the network syncing, and relaxed timing. So it can be under the 100 millisecond to the 1 second. So this is how you can do things in the RTOS. RTOS is not just it not parallel processing or the parallel threading. It's not the real time parallel threading. It's just switching between the tasks so fast and with the particular dedicated time, so that it act as a real time operating system. But it's not just a real. It's continuity, so that we can't actually we feel it out. Okay. So suppose that you have the two tasks in the RTOS for the blockchain client, and then it first switch between the high priority task, complete the high priority task within that limited amount of time that is dedicated for the high priority task, then the low priority task. So this is how it works. So if he uses the messages queues like the pre-RTOS queues to pass the data between the RTOS task and the blockchain client, different whatever the data is. So it can store the temporary data in the RAM as temp FS or SD card or F2FS system, and before committing to the blockchain, and after and then it will transfer it to that. Then it commit that on the blockchain. Okay. So there is a timing challenges in the in this as well, like in the blockchain application syncing in the Ethereum headers under the 100 milliseconds. You can have to and if the task that blockchain operation conflict with the RTOS deadline, like it takes more than the 100 milliseconds, then it can't conflict, because there is another priority task behind that, and behind that there is another priority task. So you have to switch between all those different tasks at the particular interval of time. If by chance that task didn't get completed that particular set amount of times, it has a priority of another task, then it might create a conflict between that, and so it can be a little bit of a complex thing that we have to handle with the RTOS as well.
Okay, so how would you partition memory like RAM and flash, and for a blockchain client running on a microcontroller?
Yeah. Can you just repeat the question again, please?
Yes, yes. How would you partition memory like RAM and flash for a blockchain client running on a microcontroller?
Yeah. Actually, a partition memory such as the RAM flash memory for blockchain clients on a microcontroller MCU requires a careful balance between the performance, storage, and need and MCU's limitations. First, we will discuss about the flash memory, normally known as non-volatile partitioning. Flash is used for the storing the firmware configuration data and the minimal blockchain logger. Firmware code 40 to 60% includes networking stack, for example, MQTT, COAP, blockchains, protocol, logic, and the cryptographic library, ECC, SHA, etc. Second is the configuration and the keys, 10% to 20%. It stores devices identity, public, private, keys, certificates, and the network setting in secure read-only areas. Another is the lightweight ledger, 20 to 30%. Instead of full losses, store only the essential elements such as the recent block headers, hashes, or the Markle's roots. Use circular buffers for the indexed section to manage limited space and the minimize flash wear. For example, in a 1 megabyte flash MCU, you need 512 KB for the code, 128 KB for the secure configuration, and the 256 to 360 KB for the blockchain state and the logs, recent transactions, and the metadata, etc., etc. So, depending on the parameters, we distribute partitioning is. And another is a RAM partitioning. RAM supports a routine operation, buffers, and the cryptographic computation. So, network buffers and the message queues 30 to 40%. It requires for the receiving, sending blocks or the peer data. Another is a cryptographic operation. It consumes 30 to 40%. Space for the temporary variable used in hashing and signing and the crypto some routines. Third is the system task and the stacks. It consumes 30 to 20 to 30%. Allocated for the RTOs if used, task stacks, and the sensor interference. For example, in a 128 KB RAM MCU, 48 KB for the network data, and 48 for the cryptographic task, and the 32 KBs for the OS, stacks, and the peripheral. So, additional storage, additional strategies क्या है? First, use static memory allocation to avoid the fragmentation. Imply memory pooling for the repeat use buffers. And the third is the store large or the infrequent access data in external EEPROM or the FRM if available. So when we summarize these things, so proper memory partition tailored to the blockchain needs and MCU capacity ensures secure, efficient client operation without enhancing the limited embedded resources.
Okay. So, what are the security risks when using a general purpose SBC for a blockchain application, and how would you mitigate them?
Yeah, so there are lots of security risks when you use the purpose SBC or MCU. Like in the Raspberry Pi, there is a risk of the boot. By default, the default boot process is via the SD card that lacks the built-in signature verification, allowing the attackers with physical access to the load different kind of miscellaneous firmware or upload the trojans to that, or modify the OS to steal the private key and manipulate the blockchain transactions. Okay, then there is a risk of the physical access and the vulnerabilities, like the physical access on the Pi common that is common in the IoT field deployment, enable the attackers to extract the private key from the SD card, access of the GPIO to temper the hardwares, and its impact is that it exposes your cryptographic keys like DSA private keys for the Bitcoin or Ethereum wallets or unauthorized control over the connected device. So all these are the security risk out there, but it can be handled with with enabling the secure boot in the Raspberry Pi or U-boot, and using the different other methods and a secure element, adding the external secure element to the to the modules.
Okay, so how would you reduce the size of blockchain client to run on an MCU with limited flash?
Yeah. Actually, to run the blockchain clients on an MCU with the limited flash and focus must be on the minimizing both code size and the storage footprint without the compromising the core functions like data integrity and the transaction verification. First, implement a light client model. Instead of storing the full blockchain, use a light client that only stores block headers and validates transactions via the markable proofs. This drastically reduces memory needs while still ensuring trust through the cryptographic verification. Next is the use of the lightweight blockchain protocols. Choose protocols designed for the constrained environment, such as the proof of authority POA, delegated proof of the stake DPoS, that eliminates the need for the energy intensive operation and the large data code bases. Avoid POW based on the system entirely. And the third is, which we have to consider, is the modular code architecture. Strip down the client to essential components, block header, parsing, transaction signature verifications. It is also very important. And third is the peer-to-peer communication. Basic, omit full networking stacks, wallet, UIs, minimizing the logic are the smart contract engines. And the fourth is the optimized cryptographic libraries. Use embedded optimized crypto libraries like micro Cs, TinyCrypt, or the BRSSL, which offer essential functions, for example, ECC, SHA-256 in small footprints. Link only required algorithm at the compile time. And fifth is the compiler and the build optimization. Use link time optimization, LTO, dead code elimination, and the size focused compiler flags like OS to reduce binary size, remove debug symbols and the unused standard libraries. And six is the use external flash or the EEPROM if available. Offload non-volatile data, for example, block header, configure file to external flash to free up the onboard flash for the firmware. So in summary, we can combining light client logic, minimal consensus, lean cryptography, and the optimized firmware, a blockchain client can be shrunk to fit a MCU with the flash sizes as small as 128 KB, making secure blockchain operations feasible for the IoT devices.
Okay, so which communication protocol would you prefer for remote blockchain based nodes, and why?
Yeah. When choosing the communication protocol for remote blockchain-based nodes, the selection depends on the power availability, data bandwidth ranges, and the network reliability. The most commonly considered protocol are the LoRa, LoRa, Wi-Fi, and the Ethernet, each with the distinct advantages. First, consider the LoRa, long-range radios. It is ideal for the low power, long range, low data rate applications. LoRa operates over the several kilometers with the very low energy communication. Its consumption making it perfect for the solar powered or the battery operated blockchain nodes. It remote for the rural areas. However, LoRa's limited bandwidth 0.3 to 50 kbps means it's best suited for the lightweight blockchain client that transmit only the metadata. Block headers are the verification results, not full transaction or the blocks. What is the use of the LoRa? It is used, nodes are in the remote area, power is limited, only small payload, for example, hashes, IDs, proofs are the exchange. Now we discuss about the Wi-Fi. Now Wi-Fi offers high bandwidth and the widely supported by the SBs and some MCUs. It's suitable for the short range applications where powers is the very moderately available. For example, solar with the battery or the backup. Wi-Fi enables full node communication if needed, but consumes significantly more power than the LoRa. It is a good middle ground for the semi-urban edge deployment. Use of the Wi-Fi when medium data exchange is needed, then you can use the Wi-Fi. When the power supply is moderate, you can use the Wi-Fi. Infrastructure, routers, access points available, so you can use this one. Now, we will talk about the Ethernet. Ethernet provides stable, high speed, and the secure connectivity ideal for the stationary grid-powered blockchain nodes. It is suitable for the gateway nodes that aggregate data from the multiple low-power clients. Where we use the Ethernet, actually where power and the infrastructure are not the constant, you can use this one. High uptime and the bandwidth are needed. Secure, high throughout the connections are required. So, for the remote, power-sensitive deployment, LoRa is preferred. For the mid-range, smart nodes, Wi-Fi works well. For the gateway or the full mode operation, Ethernet is the most suitable. A hybrid approach often yields the best system efficiency and the reliability. That's all.
Okay, so what strategies would you use to ensure long-term reliability of flash storage used for blockchain writes?
Yeah, so for the flash storage for this black blockchain like the SD card or eMMC on the Raspberry Pi, it's often prone to wear due to the limited read and write cycles of the flash storage. Okay, so the for the black blockchain applications with the frequent read and write and transaction logs, the block headers on state updates, there are lots of read and writes happens, and if you go for these frequent read and write kind of task on the SD card eMMC, due to the limited read and write cycles, it is not good choice for that. Okay, so the strategies, now let's talk about the strategies. So what are the strategies we can use for such things? So one of the good approach that can employ the flash friendly file system F2FS, that can flash friendly file system, or ext4, which is optimized to distribute the write cycles evenly across the SD card. So even the read and writes happen so frequently, it can distributed evenly across the SD card. So one read and write on that particular block, it's not doing that again and again on the same particular block. It is distributed evenly. So that's why we call it the flash friendly file system. Okay, so this helps you a little bit but not very good extent. And okay, so second, you can choose the high endurance storage system like you can select the SD card and eMMC designed with the high read and write endurance that has the immunity and that has the capability to and give you the option to read and write uh, with they give you the right large number of read and write cycles so that it can withstand. Or you can you can use the industrial grade with SD card that has the read and write cycle of 100 100K 100,000 Ks, or SLC based eMMC that 1 million cycles of the read and write cycles, so that you can use that. So you can use the industrial grade with eMMC or SD card. I recommend you to use the eMMC over the SD card because it give you more read and write cycle. That is a 1 million write cycle over the while the SD card give you only 100K write cycles. Okay, and uh, you can you can use this kind of a strategy. Okay, that's the options for you that you have.
Okay, okay. So my last question for this session is, how would you debug and test a blockchain node running on a headless SVC in the field?
Yeah. So for the debugging, if you want to debug and test the blockchain node running on the headless single board computer like the Raspberry Pi or similar kind of SVCs. Okay. So these are the strategies like you can do the robust logging. It is an approach by which you can configure the detailed efficient login to capture the blockchain system and events for the post uh, uh, analysis and the real-time diagnosis. And you can use the blockchain. You can enable the uh, verbose logging in the blockchain client. Okay, for the debugging level. Okay, for the encryption side, SCD encryption logs, you can do the in AES 128 before the remote transmitter to prevent the data leaks. You can encrypt the logs. Okay, and you can limit the log size to the 1 MB in the RAM to avoid the memory exhaustion. Like if there is large number of what's a large number of things need to be encrypt and that is taking more RAM. So if you're taking more RAM, then it's hard the other task and it may put the stress on the RAM. So you have to limit the log size, okay, to the 1 MB on the RAM, so to avoid the exhaustion of the RAM each for each encryption logs. Okay, you can use the secure remote access, enable the secure remote access for the real-time debugging and the configuration and the logging. Okay, you can use the SSH with the key authentications. Okay, you can use the web dashboard. Okay, and again you can use the you can encrypt all those things while doing this. Okay, you can do the network debugging, and you use the testnet or the simulation thing. So these are the things you can do.
Okay, okay. So this brings us to the end of this episode. And if you have any question, kindly post them to the comment section. We will get back to you in our next session. Thank you. Thank you, everyone.
Thank you.
Thank you.
Thank you.